Yeah, so I'm Keegan Owsley. I've been with BDB for about 6 years now within the Advanced Technology Group, and I'm so excited to be here today to be able to present to you some of the work that we've been working on for, well, yeah, 6 years, or in some cases more, and to finally bring them into fruition. As Bob hinted, we've finally launched this new product. It is available. You can go see it at our booth, and it has all the technologies we're going to talk about today. I'm going to focus on the CellView image technology piece. There will also be a little teaser of spectral unmixing. If you would like more information about spectral unmixing, I encourage you to visit the booth. And then Jake will take over and talk about some of our new dye advancements. Yeah, so without further ado, let's get into CellView. So some of you may be aware, last year we published this article in Science discussing a high-speed fluorescence image-enabled sorter. And the way it worked is essentially CellView adds a new imaging laser to your system. And any detector that collects data from that laser produces an image. Now, it was important to us, our primary expertise is cytometers, not microscopes. And so when we were thinking about how we can build new functionality into these systems, our focus has been how can we enable our existing architectures to basically upgrade and get these new features. And so this technique I'm about to show you is a way to turn a regular cytometer with PMTs, with APDs, with photodiodes into an imaging system that has all of the same capabilities of a regular cytometer plus imaging. And the way that works is pretty cool. So first of all, you can see the citation there. If you want to go into detail, the science paper will go into detail for you. But first, a quick reminder how cytometers work. Bear with me, this slide deck was written for engineers who are not as familiar with cytometry, so this is like a baby's first cytometer drawing, but hopefully it'll put everyone on the same page. So with my crude drawing here, I have a cell that's flowing down from the top. He's entering a blue laser, and then light comes off the cell. We collect that onto a detector. It produces a pulse, which looks something like this. You can imagine as the cell enters the laser, the rightmost edge of the pulse starts to rise. As it sort of gets centered in the laser, you sort of taper off. And then as it exits the laser, it falls down to its baseline level, right? And in a regular cytometer, this is what you get. We report basically how much total area is underneath the pulse, what was its height, what was its width, but that's really the extent of what you can get. Maybe if you're really clever, you can extract a couple more things, but you're not going to get a lot of information about how the fluorophores and it was just distributed in the cell and where the light's coming from. Now, if I can describe in one picture what our system is doing, we're pixelating the laser. So you can imagine that instead of entering a single laser, it enters actually an array of n spots, say 100 spots. Each spot in that array is blinking on and off at a different frequency, which causes all this extra information to appear on top of your pulse. You can imagine that fluorophores on one side of the cell are passing through these slower blinking spots, and so they have slower modulations on the pulse, and vice versa. Fluorophores on the right side of the cell are going through the faster blinking spots, and they will have faster modulations on the pulse. That pulse on the right is actually a real pulse collected off of one of our systems. And if you do some math to back everything out, that's the image that you can extract out of it. Now, I realize that this is sort of arcane to probably a majority of this audience, so I'm going to walk you through an analogy. This analogy kills with the engineers. I realize most of us here are scientists, so bear with me. Hopefully you can get something out of it too. But before we get to the analogy, I do want to show some cool graphics that our marketing team has produced. Essentially, one of the key physical insights that we've produced is we're using this acousto-optic deflector to turn one beam into 100 spots, and then we use some optical interference techniques to make those 100 spots all blink at different rates. And again, if you're interested in the details, I encourage you to check out the science paper or come by the booth. But that's the gist of how it's done physically. Now, if I can get into an analogy. So there's this analogy that we are borrowing from telecom. Basically, there's this technique that your cell phones use to be able to all talk to the same cell tower at the same time. You can imagine that they're all sort of shouting into the void, right? And that if you're a cell tower, you're hearing everything at the same time. That's a problem, right? So how can you build a system that can talk to all these different cell phones at the same time? Well, there's a technique called orthogonal frequency domain multiplexing, OFDM, and that's essentially what we're doing. So if we go back in time a little bit to early cell phones, like think 2G era of cell phones, they did something called time domain multiplexing, where a cell phone would get a slice in time where it was allowed to talk, and it was supposed to be quiet during the rest of the time. So you can imagine cell phone 1 would talk, cell phone 2 would talk, cell phone 3 would talk. The cell tower would get all of those signals overlaid on each other, and as long as everyone's playing nicely, there's no overlap. But you can quickly see how this doesn't really scale too well, right? If you've got thousands, tens of thousands of cell phones that are quiet most of the time, what do? You're wasting a lot of your bandwidth. So the idea was, instead of just everyone talking at the same time, they could do it in a special way. Basically, everyone could talk with what's called a modulation. Their speech would be, would have a special signal that, in this analogy, is colored. So when they're received by the cell phone tower, it's a mixture of colors, but that is performed in such a way that the cell phone tower can mathematically unmix them afterwards, right? And those colors actually directly translate into the frequency of modulation. So if you have one cell phone, its signal is modulated at one frequency, another cell phone modulated another frequency, you can mathematically back that out. And so that's what they're doing. And we're doing essentially the same thing. The different pixels of our imaging system are all talking with a different frequency. The PMT is going to collect all that at the same time, and then we're going to do some mathematical tricks to pull it all back out and separate them into an image. Right, so I'll make sure I didn't skip anything. Yeah, okay. So what does that get you? Well, on our actual instrument, what that means is that every single event, every single particle that enters through your cytometer also gets an image. Not just one image for every detector detecting light off of that laser. So you get side scatter images, you get forward scatter images, fluorescence images, and also this new light loss detector, which sort of you can think of as analogous to like a bright field microscope image. And you can imagine if you're going at 10,000 events per second, that's a lot of data. 130 kilobytes per image times 10,000 images per second, it starts to add up quickly. So, that's something that you have to consider when you're using one of these systems. Make sure you have a plan for where you're going to put your data. But yeah, every single particle, you get an image, multicolor image. It's roughly analogous to somewhere between a 10x and 20x microscope. Now, that's a very rough analogy, so I'd take it with a grain of salt. But if you're interested in the specifics of the imaging resolution, the smallest two particles you can resolve from one another on the order of 1.5 microns with this specific iteration that we've released today. Right, so here's the overview again. A cell goes through a beam profile. We get a complicated waveform on our detectors, and then we do some math to turn that back into an image. Yeah. So what does that mean practically, right? This thing at the end of the day is still a cytometer. You're still getting area under your pulse, you're still getting height, you're still getting width. You still get your traditional plots that you always had, but now you can mouse over every plot on your regular cytometer and get the picture of the cell that generated that dot. If you've got an extremely heterogeneous sample, that means that you can start to ask really subtle questions like, where exactly do my singlets that are elongated and weird looking end and my doublets begin, right? Or whatever. Also, you can do things like gate on a population and just look at a big collage of all those cells, right? And yeah. But looking at pictures is great and all, but really what makes this technique powerful is its compatibility with sorting technology. These waveforms enter our system, and the hardware will mathematically compute a whole bunch of imaging features in real time, and then you can sort on those imaging features and basically perform downstream analysis based on image analysis that you could never do before. So here's a list of the imaging features that we're able to sort on for now. All of these features are available on the instrument. You can put them on, if you can put it on a plot, you can draw a gate, you can sort. That's the philosophy here. I've kind of put the official name of the thing and then also how you would interpret what it means. We've tried to stick to the mathematical definitions for the official name. Now, keep in mind that the reason this list is what it is today is that a lot of work was put in to make sure that we could compute them really, really fast. Obviously, if you're going to sort 10,000 events per second, you better be able to compute some of these really complicated imaging features that fast. And so that's the reason the list is what it is today. If there are things that you know you would love to sort on because you do image analysis yourself and they're not here, I would love to hear from you. So let's dive into one specific example, eccentricity. So if you look at that top cartoon here, basically what we're measuring is how elongated is the distribution of signal. So irrespective of how large it is or how bright it is, we want to know if you have a long axis and a short axis, how different are those axes, right? And you can use that to do all sorts of very interesting things, like, well, you can do basic doublet discrimination, which is great. You can already do that with width, but you can do it to a better extent with this. You can also do really interesting cell morphology questions. Sometimes your cells aren't actually spheres, even though they're suspended, and so sometimes those cells are interesting. You can identify clusters of cells. Yeah, and you can actually, so down below, we've shown an interesting cell cycle set of data that was published in that science paper. Again, encourage you to go check it out. But it's one thing to find examples of a cell in each phase. It's quite another to then sort on them, and that's what we've done. So you can take your traditional plots. In this case, we've got just a few colors, but then they're all augmented with imaging parameters for each of those colors, and start to gate on them just as though they were regular parameters. So you can plot area versus eccentricity, radial moment, whatever you want. And if you start digging down, you can start to separate cells in different parts of the cell cycle. That hopefully isn't too surprising. But then, of course, the real deal is that you can sort it. And so after sorting, these are sorted onto a slide. We can pop them into a microscope and just validate, hey, this thing really works. You can sort them. You're going to get good purity on your really funky image parameters, right? Right, so that's basically in a nutshell what CellView imaging technology gives you. So next, I'd like to invite Jake to come up. He's going to talk to you a little bit about Spectral, and then dive into the dye story. And again, if you're interested more about Spectral, come by our booth.
So thank you very much, Keegan. So my name is Jake Ravenstein. I lead the dye development team at BD. So my team has a team of flow cytometrists that work very closely with the chemists, and our ultimate goal is to develop new and better dyes that work in flow. And as you can see, flow is changing quite a bit. So I'm going to get to in a little bit how that is entirely changing the paradigm of how we think about dyes. So first, it's important Keegan went through CellView and the amazing technology that is. It's also important to remember that on FACSDiscover, we have a fully enabled spectral system as well. So I'd like to jump into that first and talk about that. So we're calling it BD Spectral Effects. It's everything that you see here. It really is optimized hardware. It's full spectrum optics. It's the unique algorithm that we have for unmixing. It's a next-gen QC system that we have, and I'll talk a little bit about that. And then guided workflows to make it all easier. So Keegan, again, did a really nice job walking through the image technology that you see on the left. So also on the same instrument is the fully spectral, ground-up built system that you see on the right. So Bob mentioned we've got 70, he didn't mention the number, but we've got 78 detectors total on this system. I'm not going to go through the individual laser lines. You can see that on the right. But a lot of work was done here to balance what is the right way to break up the spectrum, what's the right way to take advantage of differences between dyes, but then also you want to maintain sensitivity in that detector and make the data meaningful and valuable. So taking that one step further, again, ground up built system for fully optimized spectral. We've taken a modular approach with the optics. So we do have a modular approach using APDs. Again, you can see the schematic of how that's handled on the right. And really the design here is meant to reduce signal loss as you're adding detectors to the system and measuring more of that spectrum. Again, really quickly, I'm going to touch on next-gen setup. So this is our first instrument that has an onboard LED combined with a setup bead that will do the daily setup. The onboard LED enables calibrated gains to be used, which makes it a lot simpler and a lot more reproducible from day to day. And we're not measuring Q and B anymore. We have a new metric for limit of resolution. And you combine all that together, and really what I'm trying to say here is the instrument has a lot more detectors in it. The instrument's going to set all those up for you, and it's trying to achieve the right balance between dynamic range and sensitivity for each detector. So at the end of the day, you do get daily settings that you can use. All of the dye data that I'm going to show you coming up was used with those settings. They're going to work for most applications. You can tweak them if you really want to, but the default settings worked for everything that I'm going to show you moving forward. So I know that was just a little snippet. It was really a transition as we go into the dye story, which is where I live. If you do have more questions on the spectral aspect of this instrument, I would really encourage you to come down to the booth, talk to us, grab us. The data that you're going to see, and then Bob's talk tomorrow, the data really is amazing. It's a fantastic instrument. So you can see from the title here, we're working on blue and yellow dyes, yellow-green dyes. It's been a challenge for years, and I'll be honest, the industry has done a really good job kind of avoiding the cross laser that we see with PE and PE tandems. But we've done that at the cost of reduced number of floors that we can actually look at. So if we jump into, I've been doing dye development for a number of years now. And spectral and CellView, we'll get to that later too, has really changed the paradigm and changed the way that we think about developing dyes. So if you look historically, we're biologists. We want to look at more. We want to look at more things in the sample that we have. The way we typically do that, or the way we have done that in the past, is you add a detector. You add a new dye, you add a detector, you optimize a filter for that detector or for that dye. Advancements in that technology led to high parameter flow, and that was a leap for the field. But really, the shift that we've seen in the last 5 years has fundamentally changed kind of how we're thinking about doing dye development. And to me, it's not really about looking at the spectrum and going, OK, there's a gap here, let's fill that gap. It's really about how do you best design a whole family of dyes for a fully enabled spectral instrument, and then keeping CellView in mind as well. So really, this goes to what I just said. I mean, it was a unique time at BD. So we had CellView that was in development. We had the fully spectral system that was in development. And we had the chemistry that's behind the dyes that I'm going to tell you about, all in development at the same time. So it was a really good chance for us to take a step back and go, how do we do this right? So we took a very novel approach here. It's something different than we've done for any other dye development. And we basically, knowing that we had a fully spectral instrument, we basically white spaced blue and yellow-green. I'm going to give the chemists on our teams a whole lot of credit. They generated hundreds of small-scale prototypes just so that we could acquire data on them and get data on things like spectrum and quantum yield. We then did a lot of computational work with some of the other teams at BD. And what's important to realize is we did that computational work in the context of the other laser lines. So if you look at UV, if you look at violet, and you look at red, we tried to figure out what is the combination of dyes that works best with all of those other dyes off all of those other lasers. So I'm happy to say that where we landed and the roadmap that we are targeting is on the left. So what you see on the left is a fully optimized family or palette of dyes that will work and has been optimized for our fully spectral system. What's really great about computational work is you can build in constraints or you can compare different options. And where we've landed is the ideal scenario where you've got the full family for spectral, but you've also got legacy positions built in there as well. So if you're on a conventional instrument or you're using an A5, you're still going to have dyes, better dyes to use that fall into that. So some of these dyes have started to hit the market already. So Real Yellow 586, Real Blue 780, and Real Blue 545 are in the market. But they come out kind of individually, from your perspective. So I'm really happy that we get to be here today and tell the whole story and the value that this is going to bring. And what I'm going to do is maybe a little bit different than a normal commercial talk. So rather than focus on each dye and tell you that I'd rather have you run 586 instead of PE or 780 instead of PE Sci 7, I'm going to show you some of the data that we have here on these dyes. I'm also going to show you some prototypes that we have in development, because the story that I really want to tell is not about individual dies. It's about the value that this overall roadmap is going to have. And I liken it to when we expanded all the brilliant violets and all the brilliant ultraviolets and what that enabled for the flow community. I think we're doing something similar here, and I'd like to give you a sneak peek of that story. So before we jump into the actual data, I want to just kind of level set with a lot of plots are going to look this way. So I'm going to level set with what we're looking at. On the left, we've got a normalized emission profile. I know everybody knows what that looks like. That is the normalized emission profile from FACS-Discover. So for the dye that I'm going to show, that is what you see off every single detector on that instrument. On the right, I'm going to show you what is labeled as CD4 overlays. And so dye development's a little bit different. We don't jump into multicolor right away. I'm going to make a bold statement that about 80% of what I need to know about a dye I can get from CD4 or using CD4. One system that we use is we overlay single color CD4s with an unmixing matrix that is appropriate for both of those dyes. And that's going to tell us how two dyes play well together, assuming everything is equal, including antigen density. So the first dye I'd like to talk a little bit about and try and provide insight into the value in the roadmap is 545. So 545 is a dye. I'm not going to tell you to run that instead of FITSI. Legacy instruments are not going to have a position for that dye or a filter set for that dye. But that is part of the fully optimized spectral roadmap. And a huge part of that is providing more options. So here we've got FITSI and 515 that are run together. Those are very, very similar dyes. You can see what that looks like if you do the CD4 overlay on the right. But by shifting the spectra just slightly, there we go, and using something like 545, that's the kind of resolution that you can get. So more options in that fully optimized roadmap give you better combinations that you can use. And you can see you dropped the similarity score from something very, very close to 1 to something down below 0.5. So let's focus on like the 780 position. So everybody's familiar with PE-Sci7. This is the dual excitation that I've talked about before. We have launched RealBlue 780. You can run that with PE-Sci7 in the CD4 overlay. And I've got a friend and colleague who, as I was showing some of this data, said, look, that's not entirely realistic. I would design a panel very differently. And I would use PE-Sci7 on something with lower antigen expression. And I agree. If I was doing panel design, that's 100% what you want to do. But this is a tool that we're using so I can compare that combination to this combination. And this is where it's going to shift a little bit, and I'm going to start to show you some prototypes that build value in the overall roadmap that we're striving for. So what I'm showing here is Real Yellow 780. It's a prototype. But I'm showing you this because if we can achieve this kind of data as we look at all of the blue and yellow-green pairs, that's a game changer. Oh, I think I went too far. So the other aspect of the roadmap is that we're expanding both of those families. I mentioned before we've dealt with it for years, but we're not running what we could be off of the blue and the yellow-green laser. If you look at the blue laser, and we're going to talk about expanding the blue laser, current scenario is we've got Brilliant Blue 700, and I just mentioned RealBlue 780 in the market. Some of the dyes that we put out are going to be alternates for legacy positions. So if we look at the 700 position, everybody knows Per-CP Sci 5.5. Everybody loves and hates Per-CP Sci 5.5. It's kind of the poster child for a dye that emits everywhere. A few years ago, we did develop Brilliant Blue 700. The goal there was to reduce the yellow-green cross laser. And you can, you wouldn't do that on a conventional system, but you can on a spectral system run both of those together. So what I'd like to show you is another prototype, RealBlue 705, and the kind of data that we can get with the technology that we're using for dyes nowadays. So not only have we reduced the yellow-green cross laser, you'll see there significantly, we've also reduced the violet and the UV cross laser. And little wins like that, my goal with dye development is little wins like that are going to add up. I mean, when you're running 30, 40, 50 colors together, any kind of reduction in cross laser or spillover that you can get, that's going to add up across that entire panel. So you'll see the gains in the SSM right there, 705 compared to 700. So I just showed you, 705 is a potentially better alternate. But now, again, going back to that fully spectral roadmap, let's look at what happens when we expand everything. So I'm going to show two more prototypes, RealBlue 744 and RealBlue 820. And I'm going to give you a caveat right now. 820 is a very early prototype. But if you run all those together, what you end up with is the normalized emission profile on the top And right off the bat, I want to address two things that I know people are going to jump on. So 820, very early prototype, does still have a lot of residual. So fundamentally, this is a new dye chemistry. It is not polymer technology. But fundamentally, to get a Stokes shift from 488 all the way out to 700, it is still fundamentally a tandem chemistry. So you're still going to have things like residual. And as much as I hate to say it, you're still going to have some cross laser of acceptor that we are going to have to manage. The residual that you see there in the blue for the 820, it's such an early prototype that we will fix. So I'm going to do like the Jedi mind trick and go, don't pay attention to that. But the red laser, you do see that. And that is real. That is something we're going to have to manage as we move forward. That's just a function of tandem chemistry. But what I really want to focus in on is, I mean, look at that. In that blue laser, you've got 4 dyes that we've put in just over the space of 100 nanometers. And if you look at the data down below, so the very first plot, the 705 versus 820, that's the best case scenario, the two that are farthest apart. The other 3 plots are really kind of the neighboring combos that you see. So 705 against 744, 44 against 780, and 80 against 820. And if we can fill out the blue and yellow-green lasers with combinations that play as nicely as these do, it's going to be fantastic. So anybody who's used Real Blue 780 knows that that's a very, very bright dye. I can tell you 705 and 744 are even brighter. So again, it goes back to the point. Even though I'm showing CD4 here, please, I beg and plead with you, don't use those dyes on CD4. They're going to have a lot of value other places. So I'm going to stop here with the data and kind of shift, but hopefully I've kind of shown you guys through some of the prototypes and other things that we have here, the value that we're trying to achieve, again, with the overall roadmap. If you're interested in individual dyes that are available now, please come talk to me, talk to us at the booth. I'm more than happy to explain the benefits that brings now. But what I want to sell is the overall roadmap. So I do know that by showing prototypes, one of the very first questions I'm going to get is, when are these coming out? So I wanted to jump into a little bit. I know they're not all out at the same time. I'd love to put them all out at the same time. But a lot goes into their development. We don't often make that visible to you guys. So I wanted to talk a little bit about the robustness that goes into our dye development process. And as I started thinking about it and prepping for the talk, it really is, I know it's overused, but it's kind of the iceberg metaphor, right? So from your perspective, a dye launches, it kind of hits the market. Maybe there's a few TDS images that you get to see. There's marketing collateral that has multicolor and other marketing claims in it. But that's really about it. So my world is everything under the waterline. And we've got, I'll say like 14 or 15 dyes all going through development at the same time. They're all at various stages. If it fails anywhere along, then it kind of goes back to one of the earlier points. And I'll touch on that here in a little bit. But the chemistry that goes behind these dyes has been in development for a number of years now. As we've honed in on that roadmap and kind of have our target positions, we generate candidates against that and we screen. But what I really wanted to mention is, it goes just beyond the spillover and the spread and things like that we're looking at. We know that it takes a long time to put together panels, and we're looking at photostability. We know that people are using automation decks and that reagents sit out for a long time. So it's important that spillover doesn't change, signal doesn't change as they sit out. We're looking at different buffer systems and different model systems. So intercellular buffers can be harsh, fixatives can be harsh. We don't want the spectra to change because of buffer treatment or things like that. Stability is an important one. We don't expect, because this chemistry is different, but we look for dye-dye interactions and things like that. Aggregation, a lot of tandems aggregate over time. The polymer dyes tend to aggregate over time. And shipping studies. Shipping studies is a huge one. So we want to make sure that when it gets to you, it looks like it did when it left us. And I've seen data loggers before, and man, those things are scary. Like the temperature excursions that these things experience across the world, whether it's on a tarmac or in a delivery van, I don't know. So we do in-house studies looking at what happens if it gets too hot or gets too cold. And then we also actually ship. So we have them ship back to us and test it and see what it looks like. And as I said, if anything fails one of these, it kind of circles back to an earlier point. So if we have a single candidate for one of those positions and it fails, we go back to chemistry and we fix that. So I know it's not as fast. I would love to have them all at the same time too, but it's really, this is trying to drive towards what we're putting out is going to work for you. And some example data on the right. So I mentioned these are just 2 examples of some of the categories I picked, but photostability. On the left, you see an example that worked really well. That's what we're driving for. On the right, you see a candidate. That is a candidate that we failed because it did not hold up. As you increase light exposure and you increase time, we failed that one. On the bottom is an example of some of the fixative work that we do. So both of those should look exactly the same. They don't. The one on the right, obviously after, I think this was a 24 hours after being fixed, the signal drop, spillover change, so we failed that one. So just, we're looking at all these different things to make sure that once they get to you guys, they're going to work. I did mention that intracellular is something that we're looking very closely at. I am not going to go through every single TDS image. These are all just TDS images for the dyes that we've released so far. And the point that I want to drive home is these dyes and this chemistry works really, really well for intracellular. What you see here is a range of different model systems. It's everything from cytokine to phospho to nuclear targets. I know everybody has their go-to dyes when they think of intracellular staining. Everything I've seen from these and the ones that we have in development so far, I do believe that these are going to be a class of dyes that when you think intracellular, you're going to go to. So to bring it back to where we all started, image technology, CellView is new. One of the things that we're looking at as we develop blue dyes is to see if they do work for CellView. So what you'll see here is one of the prototypes that I showed, Real Blue 705. It should show up in image channel 3. And what we're looking for here is really good staining in image channel 3, but no spillover or residual that falls back into either one of the other imaging channels. So to take that one step further, we are testing all of them. So these are 2 of the prototypes and in Real Blue 780. All 3 do work. They work well. And again, they give multiple options because as we layer in now the complexity, now you're doing CellView and you're doing multicolor flow all in the same panel, if you will. So having options to pick from that work to put together a better panel adds value there. So that's really the end of this talk. I know that what we have done here is kind of show you all the individual pieces. So what I'd like to give a plug for is the talk where a lot of this comes together and you actually get to see the biology. So Bob has a talk tomorrow. It's going deep into a couple cell lineages, doing a 6-way sort, utilizing the new dyes on FACSDiscover. So I've seen some of the data from the talk. It really is fantastic. I would highly encourage you to attend. Thank you all for attending again. If you do have questions, stick around.